Okay, so last time we talked about the mole, right? And the mole is equal to what? Right. Avocado's number? Yes. Yes, so it's 6.022 times 10 to the 23rd. And it can be anything: atoms, molecules, compounds, underwear, socks, girlfriends, boyfriends, cousins, second wives. I guess you can only have one second wife, right? Sanchos. Yeah. Okay. So how would I start this problem?
By your given.
Start with our given, right? So my given is
5.06 times 10 to the 23 atoms of gold.
5.06 times 10 to the 23 atoms of gold. AU. Okay. And then what do I need to do?
And then you would use the Avogadros. So
Am I going to times it by Avogadro's number? Or am I going to divide it by Avogadro's number?
divide it.
Half of you guys say times it, the other half say divide it. So we know that 1 mole, and that's what we want to get to, right?
Mm-hmm.
So am I going to put moles on top or moles on the bottom?
Moles on top, because the grams per mole is what you're getting to, right?
Eventually, yes.
Which is
We got 1 mole.
196.7 for gold.
Okay, that's our next step. Let's get to the first one, right? So then we're going to put Avogadro's number on the bottom, right? Because we can make those atoms, right?
Mm-hmm.
So then that's, somebody told me 6 point what again?
022 times 10 to the 23rd atoms AU.
Okay. And Robin, you were saying something about that molar mass stuff or the atomic mass or something along those lines.
Right. So
Grams per
it's
mole, that's right.
it was the molar mass, so which is also the atomic mass.
Okay.
So I looked at the P table and I got the value of 196.97 grams per mole.
Okay, so I'm gonna say 197. You said, didn't you say 196.7? Or is it 197.6?
196.97.
Did somebody do the heavy lifting for me?
I got 166 grams per mole.
166?
Mm-hmm.
You got 1.7? E to the 48? Okay, so we've got to work on that one there. All right. So let's talk about that here. Okay, so when I'm entering this in the calculator, it's 1.165. And anything after that? What's the number after it? Okay, give me 5 numbers. to the what power? So, because you said you got 166, right? Somebody? Okay. To the times 10 to the 25. That's huge. Yeah, that's huge. Okay, we got to work on that. Okay, so when we're entering things in the calculator, we got to be careful on how we enter them, especially now, since you guys are using those exponents, right? So what I recommend that you guys do is multiply the numbers up top first. And then when you do your division, you type in parentheses 6.022 EE to the 23rd, close parentheses. Because you get in a habit of doing that, you're going to get the correct answer. But if you type in that multiplication and then you do division, it's just going to divide by that 6.022. That 10 to the 23rd is going to be multiplied on. So that's exactly what happened to you. So,
I have a question, Dr. Henry.
Yes.
Because the times 10 to the 23rd is the same at the given and the avogadros, does it cancel the 1022 to the 23rd?
Yes, that'll be the easiest way of doing it. You can just cancel that out. So
just be 5.06 times 197 divided by 6.022.
yeah, so this would cancel out along with these, and this would cancel out along with these. So what did you guys get down? Okay. One 1.66 times. Are you sure? Or is it 10 to the second? Huh? Yeah. So 1.66, 166 times, 166 grams.
Yeah.
Yes. If you did in scientific notation, it would be 1.6 times 10 to the second. 1.66 times 10 to the second. Because that's the same thing. Okay, is there something I can help you with? Are you guys there? Can you guys see it? Not too hard? Okay. So you guys remember how to use the mole? And you guys remember what molarity is. What is molarity? It's moles over liters. So the specific moles of solute over liters of solution. Okay. So knowing that, let me type that down. Okay, knowing that, can you guys calculate the molarity in the next problem? We'll move it up so you guys can see it a little bit better. Where's this the crew here? I showered. I don't know how. No ideas? No ideas?
I have an idea of where to start, but it melts from here, and then we have the 23.6 grams. You cancel out the grams, you have grams, over grams, right?
Okay. Yep.
But then I guess that's where I'm just like, oh,
Okay, but what are you asking for?
the molarity.
Which is what? Molarity, which is defined as moles over liters.
So I have the liters now.
Yeah, but don't you have moles? Didn't you just calculate moles? You just told me how to calculate moles. So then what are you left with? What are the units you're left with? If you cancel out the grams and you have moles on top. So then you have moles, right? Uh-huh. And then you just put the units grams per mole, right? But how do you know? Sodium chloride is what? How do you know it weighs? How much it weighs? Where did you find that information out? Or did you? There we go. Yeah, yeah.
1.56 molars or
Molarity.
or
Molarity.
molarity. Yeah.
Molarity. Yep. Okay, so let's do the math. Okay, so where are we going to start at?
The given, which is the grams of sodium chloride.
So you said we're going to start with 23.6?
Yes.
23.6 grams. Sodium chloride. What is the chemical symbol for sodium chloride?
NaCl.
NaCl. Okay. So what's next?
You'll then use the molar mass to convert to moles.
Okay, where do I find the molar mass at?
So you'll add the molar mass found on the periodic table of sodium and then also chlorine.
So how many sodiums do I have?
You have 1 sodium.
1 sodium. And that weighs?
I believe it's it's 22.990. I made an error.
23?
Yeah, basically.
Okay, 23. And that's grams per mole. And then we have chlorine,
Which is 35.45. So
5.45. And that's grams per mole. And that's, we add it together.
I
You got 58.45. It's because that 0.45 is kind of, it can be, depending on how many you have, it could definitely play a part in it. Here's not going to play too much, but you want to be safe, you know. That's grams per mole. And Heidi was saying we want moles on top. So we have that 1 mole on top. And then what am I putting at the bottom? That 58.45. Okay. So grams Ones are going to be canceled. What do we get? Anybody do the heavy lifting?
Don't you need your 200 milliliters and then converting that to liters or
We
liters?
do, but we should probably get the moles first, right? Because it'd be
Oh.
easier just to plug it into the equation.
Okay.
You got 0.403, you said? So 404. We're doing 3 sig figs, right? And that's moles. Okay. So we also have 200 mils of water. So, but we want liters. How do I change that? It's 0.2 liters. How did you get that? Did you just plug it out your? Okay, so because you know that for, okay. So we have 200 milliliters. And we know that for every 1,000 milliliters, that equals 1 liter. Or as you said, for every 0.001. So my answer would be 0.200 milliliters. There you go. Okay, so then if I want the molarity, mind if I erase this here? If I want the molarity, how do I calculate that? Okay, so molarity is going to be equal to 0.404. Okay, that's right, over the 0.2. Okay, and what do you guys get? So you said 2.02. Piece of cake? I actually put the decimal point here. This should have had a decimal point to let us know that we have 3. Yeah. So normally, in that case, you're right. It would have been just 1 if we just had the 200 there.
So how do you refer to the unit? Is it like 2.02
Molarity.
molarity? Okay.
Molarity, yes. Not molality, molarity. Not molar. Oh. Some people will say molar, right? But it should be molarity. Okay?
Got it. Thank you.
Questions? Concerns? Cat? Oh, my head's away. Sorry, it's big. Can't help it. I have to with a big brain. Different with like you see kids without their mask, you're like, you're not sick. Exactly. That's what I'm like, Yeah, it's amazing how different it looks when you just look at the size. Although it's good to see smiles. I can tell when you guys are kind of laughing at that joke, you know? Yeah, rather than when I look at you guys, you look so gone.
You just see our eyes, you just see like despair and then you're like, oh, this is
Exactly, yeah. Makes me want to cry, you know what I mean?
like good.
Okay, are you guys ready to get started on our new topic?
Not really, but I guess
It's not like it's short, right? Yeah.
I don't got one.
Did you guys get it? Good. Okay, you guys understand? You feel it? Feeling it? Okie dokie. Let me clear this. Oops, that's not what I wanted to do. Okay. So you guys remember the light bulb experiment? We put the electrodes in solutions, either it lit up or it didn't, or sort of, right? Okay. So you guys have already done this experiment, so you guys should be pretty much gotten this in your wheelhouse. But we're going to give you some of the scientific terminology. So we have a non-electrode, we have an electrode, and we have what we call a weak electrode, strong electrode and weak. Okay, so those things that aren't able to conduct electricity are called non-electrode, right? Or electrolyte. Sorry, not electrode. So you guys drink Gatorade, right? So it advertises it has electrolytes. So what would you guys expect to happen if you had Gatorade as our solution? We would expect it to light up. It should light up pretty well, right? That's what we expect. Otherwise, we'd be saying, you're cheating, right? We're paying for those electrodes. I want my money's worth, right? Okay, good. Okay, so things like water or ethanol, those things are covalently bonded. Covalently bonded means that they're sharing electrons. That also means that they're not going to break up in water and have positive and negative charges. They're just neutrally charged all the time. So we'd expect that not to conduct electricity, and it doesn't. Although we know that Kalinga water and Salinas water and Fireball water, they conduct electricity very well. Stuff that we got out of the faucet, you guys remember that? Right? Where although we did get our water from Walmart, that may explain why some of it did conduct electricity, you know, so we need to go to Walmart and said, hey, that was supposed to be distilled water. You have a lot of ions in there for it to be distilled, you know. So we know that it's a strong electrolyte if it has charges, plus and minus charges. And if those compounds separate completely, that separation completely is called ionization. Hold on one second. No, there's something that. Is that? Yeah. Okay.
Yeah. Time out. Let's go to study that. See what's wrong with that guy. Well, we watch crack addicts.
Dr.
Okay.
Henry,
Yes.
why is the ethanol not igniting with electricity? Is that, or I would have expected it to to combust.
Okay, so it doesn't combust. Well, one thing is because it doesn't get high enough temperature, and also the fact that it isn't conducting the electrons. So that circuit isn't being completed. So we don't have the electrodes here touching each other. And since there's no electrodes touching each other, you're never going to get a spark. And you need enough of a spark, a threshold spark, to get that combustion to start in ethanol.
I see. Okay. Thank you.
So is that why ions do have electricity? Because they have
Well, they
that
conduct electricity because they have that plus and minus charge, right? And so, and we'll talk about it. I'll show you it in a little more detail. But if you take a look here, you have your plus and your minuses throughout the throughout the solution. And so those plus and minuses are going to help that conduction of electricity. So it's going to pair up with the electrode and allow that stacking. And so you get the electron being transferred throughout the solution itself. And I'll show you that here in a second.
Okay.
And in the case of a weak electrolyte, so in a weak electrolyte, you're going to have some things that aren't going to separate, that aren't going to ionize. And when I say ionize, that basically means they break up to that plus and that minus charge, that solid plus and that solid minus charge. Okay, so like, for instance, this is my fist, right? So the fist is going to represent the negative charge. The hand that covers the fist, that's going to be the positive charge. So normally when we think about an ionic compound, it's neutral. It comes together and they balance each other out completely, right? So, but when we put in water, it separates those charges because water has characteristics, it's polar, right? Meaning that, I keep pressing the wrong button here. There we go. Okay, water, which is H2O. So they're sharing electrons, but we know that when they share electrons, they share unevenly, right? And so they make it seems like they're kind of charged, but not completely charged. So oxygen is going to be what we call partially negative. And then hydrogen is going to be partially positive. So this symbol here is delta, the lowercase delta. Okay, so we know that like sodium and chloride, sodium is positive, it's solely positive, right? Chloride is all negative. They come together, right? They balance each other out. Well, what water does, it gets in between them, and water, the oxygen will surround the positive one. So what oxygen will surround the positive one, and then the hydrogen will surround the negative one, right? And so water is kind of like a home wrecker. Comes in and say, hey, baby, you don't need him. He's no good. You know, I'll take care of you. And then water does the same thing to the other partner. And then so it separates them. And then when it separates them, it puts them in solution and keeps them away from each other. So they don't interact with each other. They're all free. Yeah, they're free, hanging out with water, right? Okay. So in the case of a weak electrode, you have some of them that are still like this, that are still connected. And then you have some that are separate, okay? And then that's what you kind of see here. It doesn't show it well, but that's together. And then you have this one separated. This one is separated. This one is together. So throughout the system, you have things that are together and then some that are separated, okay? So electrodes are those wires or those cords that are going to be conducting the charges, right? So they're allowing the charges to enter and leave. And then you have electrolysis is just the process of things going, the electricity being transferred through that system. That's electrolysis. So you guys have heard of electrolysis before? Like when your hair being removed?
Oh, I was thinking hydrogen gas with the platinum electrodes.
Yes, that will work too. You guys have not heard of electrolysis with hair removal and stuff like that? Well, is that not quite laser, but they actually use electrical current to shock the hair out of you. So. Yeah. Okay, so here we have potassium chloride. So potassium chloride normally is connected. So it's an ionic bond. And then as soon as we put it in water, it separates. Okay. Now when it separates and we put in our electrodes, this is our negative electrode, this is our positive electrodes. So then the negative electrodes will attract the positive, right? And then the positive electrodes will attract the negative. So they'll get organized, right? And then as soon as you start the current going, then what happens is that this guy, which is now negative, attracts that positive. Well, then this is going to attract that negative. And then back and forth, back and forth, back and forth, so that the electron is able to be conducted across that plane. So it's just going, okay, this positive gets an electron, it carries that electron to the negative, back and forth, back and forth. So then you're just shifting that electron to the solution. Okay. And so because you have that positive and negative, you have that altering state, where if it was neutral throughout the entire thing, it wouldn't be able to conduct electricity. Okay. So strong electrodes, you're going to have total ionization or nearly total ionization, meaning that they almost completely all separate. A weak electrode, you're going to have partial or limited ionization or dissociation. And a non-electrode, electrolyte, you're going to have no conduction at all, okay, because you don't have any ionization. Okay, so here's an example. Sodium chloride. So if we put sodium chloride solid into water, it dissociates into its complete ionic forms. We have the sodium ion and we have the chloride ion, right? And the water is keeping them separate. Okay, in the case of copper 2 chloride. So if we put copper 2 chloride solid in water, we'll have copper 2 plus ion, and then you'll have the chloride ion. And here you'll notice that the chloride ion has a coefficient of 2, because the reason that they're attached is because the plus charge on the copper. Okay, so let me give you an example. Let's see. Jace. Okay, Jace is copper 2 plus. Okay, so you hold one of his arms, you hold it over his other arm. Okay, now in solution, when they're solids, they're like this. When you guys are solid, they're solid. Okay, so you guys see that? You can, yeah, we want everybody to see, so you don't work your way around so everybody can see you. Okay, now you guys see that they're connected, right? They're negative. He's positive. Yeah, okay. So, as soon as water comes in and separates. Now, are these two connected to each other? So they're individuals. So that's how we have 2 of those ions. These 2 negative, chloride, and then you have copper all by himself, right? Okay, you guys can go sit down.
You're the homework for this time.
That's right, I'm a homework. I'm good at that, Yeah, baby. So, okay. So anyway, the key is that now you have 2 independent ions. They're not connected together. Okay? Good? Okay. So this is just kind of showing you what really happens in solution. So if you add a whole bunch of salt to water, so long as you have enough water to surround those ions, it's going to dissolve, right? As soon as you exceed that amount, that salt will stay solid at the bottom. You guys have seen that before. Have you guys had to gargle with warm, salty water? And as a kid, you just dump all that salt in there, and then there's these granular salts at the bottom, granular salt at the very, very bottom. Cannot talk today. So if you kind of pay attention to what's happening, the red represents oxygen, the white represents hydrogen. So in the case of the negative charge, the whites are surrounding it because the hydrogens are partially positive. So they're going to orient themselves towards the negative charge, right? And then if you take a look at the positive charge here, the red are surrounding it because the oxygen is partially negative. So it's going to surround it. So that's how water disrupts it, because water is bipolar, right? It has that partial positive and that partial negative. Okay? As I said, player, baby, you know, so. So this is just showing us exactly what happens in the case of copper 2 chloride. So you guys can see, I'm not lying to you, it was a solid before, right? And then as soon as we dump that in there, we get it to dissolve. The reason why it dissolves is because water goes in, breaks up that happy home, right? Okay. So I want you guys to write the dissolving equation for potassium sulfate. Okay, so we want to start off with what we're given, Okay, so we have K2, SO4, and we know that that's going to be a solid. We're going to be adding it to water. And we put water here instead of having water react with it, because water is just going to be carrying it into solution, right? And so we want it to be aqueous, right? You guys notice that when it went from a solid to AQ. Okay, so then what's going to happen when I put it in water? They're going to separate. Okay, so I'm going to have 2. Okay, AQ. And okay. AQ. Good job. Okay, the second part, ions. So write the ions presented in solution for calcium nitrate without writing the dissolving equation. So we just want the ions. What ions are you going to get? Going to have calcium. Okay. Okay, and okay. Plus what? Okay. That's it. My head's still in the way. What? Simple? Not too hard? Good. Okay, so when we talk about an acid is just a special case where we get the ionization. So in this case, we're going to get that hydrogen ion, that H plus, which we know binds immediately to water to form the hydronium ion, H3O plus. Okay, so in this case, this here is a generic form of an acid, that HX. So here, the H is going to go to the water. It's going to form the hydronium ion, and we're going to get the conjugate base, or that negative ion. Okay. So clear. So here, if we have a monatomic, so X here is going to represent a monatomic ion. So we have hydrochloric acid. So then if we have that hydrogen chloride rolled into water, then we get the hydronium ion and we get the chloride ion. Okay. Now, if it's a strong acid, it's going to happen immediately. As soon as we put it in solution, it's going to just totally separate, right? So as soon as that hydrogen chloride is boiled into or bubbled into water, it separates into the ion. Okay. And so we get the formation of those ions. So it dissociates. Okay. And that's the characteristics of strong acids. Okay. Same thing happens in the case of hydrogen, nitrogen trioxide. When it's boiled into or bubbled into H2O, water, then it's going to form the hydronium ion, and this is a hypo. And we're catching a lot of these. Hold on. Okay, so it's going to form the hydronium ion and the nitrite ion. Nitrate. Okay, so this is an example of a polyprotic acid. Polyprotic basically means multiple H pluses, right? So in this case, we have two H's to give, right? So in this case, one of the H plus goes with the water to form the hydronium ion, and then we get the hydrogen sulfate. And then eventually the hydrogen sulfate ion is going to donate its H plus to water, and then it's going to get the hydronium ion, and then you're going to get the sulfate ion. Okay. So if we have carbon acids, carbon-containing acids are weak acids. The reason why they're weak is because they like to keep that hydrogen attached to them. So this is an example of acetic acid. Well, acetic acid is going to, it's going to be able to ionize, but it's going to ionize weakly. So some of them are going to separate and form the hydronium ion and the acetate, but the bulk of them are going to remain in this form. Okay. So carbon acids are weak acids. So they're going to not ionize completely. The bulk of them will be still connected, meaning that the hydrogen stays connected. So this hydrogen is going to stay connected. Only a few of them, only a few, are going to be able to separate, okay, and ionize. You guys got that? Okay, so weak acids have limited ionization. Where? Because it stays attached. The hydrogen will stay attached to that, to the compound. So strong acids completely ionize or almost completely ionize. So they're going to separate. Okay. Okay, so strong acids, they're going to ionize almost completely. So then that means that you're going to get what we call a major species and a minor species. Okay, So if we don't get complete ionization, that means that, but it's almost completely, you're going to get a lot of the ions and then just a little bit of the compound still together. Okay. So the major species of a strong acid is going to be the ionized components. The minor species is the unionized molecule. And I'll show you what I mean here in a second. For weak acids, it's going to be just the opposite. Its major species is going to be the unionized, and the minor species are going to be the ions. Okay, so so much better. Okay, so here's an example of hydrochloric acid. So hydrochloric acid is a strong acid. It completely ionizes. So if you take a look, that's the chloride ion, and then this is the hydronium ion. So all of the hydrochloric acid has completely dissociated. Okay, so you got plus minus charges, plus minus charges, plus minus charges, plus minus charges throughout the entire solution. Okay, now in the case of acetic acid, this here is acetic acid molecule, right? This here is an acetic acid molecule. This here is an acetic acid molecule, and this here is an acetic acid molecule. This is the ion that is formed. That in a different color. So this is the ionized version in pink. And I forgot one. Okay, so if we look at this, we have 1, 2, 3, 4, 5. 5 molecules that didn't dissociate, that didn't ionize. We have one that did, right? So that's an example of a weak acid. Okay, because that ionization is going to cause that electrical current through. So weak acids are going to conduct electricity poorly, where strong acids are going to be able to conduct electricity. Great. Great conduction. Okay, you guys got that? Good. Good, good. Okay, so let's talk shop here. Okay, so we have hydrofluoric acid and we have hydrochloric acid. Hydrofluoric acid is a weak acid. Hydrochloric acid is a strong acid. So what do you think is happening in the case of hydrochloric acid? Are we going to get total ionization, separating completely? Okay. So, because we know strong acids totally separate. Okay, so hydrochloric acid totally separates. Hydrofluoric acid is a weak acid. So what is going to be the major species there? The one that's still connected, right? Okay, so the unionized, right? So unionized. So the majority of the species are going to look like this. It's going to be connected. Okay. So why do you think that's the case? Aren't both of them halogens? Shouldn't they both behave the same way? So what do we know about fluoride or fluorine?
It's
What was
the
that?
most electronegative.
Yes, it has the highest electronegativity. And electronegativity means you want to do what? Or you're taking the electron so you can be
Yeah.
like another gas, right? So in this case, you're saying to hydrogen, you stay right here. You cannot separate because I'm stronger than you. You're going to obey me. You need to be right here next to me. Where chlorine has a weaker electronegativity, it allows for that hydrogen to kind of escape. Where chlorine allows for the hydrogen to escape, fluorine won't. Fluorine will keep it right next to it because it has such a strong electronegativity. It doesn't deionize completely. Most of them will stay in contact. So if you kind of think fluorine is kind of like that really abusive boyfriend that doesn't let his girlfriend go anywhere, right? Really, really jealous, abusive boyfriend. You stay right here. You can't go to the bathroom by yourself. I've got to watch you go to the bathroom. That type of fluorine. Fluorine, yeah, fluorine. Kind of a bully. Has this little bit of a complex because he's so strong. He's like, his personality is so strong. You can't move. You can't do anything you want to, right? Yeah. It doesn't want to dissociate. Yes. That's right. So it's a weak. So fluorine is going to be a weak acid, where fluorine or hydrochloric acid is going to be a strong acid. Okay. Hydrofluoric acid is going to be a weak acid.
So does that extrapolate to other acids where stronger acids have lower electronegativity values?
For the most part, yes.
Okay.
Except for carbon acids. Carbon acids are always going to be weak. Okay. Okay, so then in the case of, so this basically just kind of is a table showing us that. So we know that hydrochloric acid is a strong acid. This is what the formula looks like. This is the conventional way of writing it. If we look at the solution, if you have a lot of them in solution, by having a lot, it keeps some of them together. So we have 79% of them separated. Where if we dilute that solution, it allows more of them to kind of get free, right? And then so we have 99+% that is separated, right? That's ionized. Where if we look at hydrofluoric acid, when it's really packed, only has 9.6% ionized. So very, very little is going to be ionized. And then if we dilute that, then we get 22%, but still 22% compared to 78%, that's still connected. That's a huge difference. So these guys are, hydrochloric acid is going to be good at conducting electricity, and then hydrofluoric acid is going to be poor at conducting electricity. Okay, and this is just showing us the equation. Our major species for hydrochloric acid are going to be the ions. Our major species for the hydrofluoric acid is going to be the compound. Okay. The minor species is going to be for the hydrochloric acid is going to be the compound. The minor species for the hydrofluoric acid is going to be the ions. So minor meaning less or lower, less than, right? Major meaning more or greater. Okay. Okay, so these are 7 strong acids. Nitric acid, sulfuric acid, hydrochloric acid, hydrobromic acid, hydroionic acid, chloric acid, perchloric acid. Yes. It's pretty strong as well. Yes, I believe so. Yeah, all acids you should be extra careful, right? Especially strong acids. Okay, so if it is so this acid is called what? You guys remember? Was it sulfurous? This is sulfurous acid, right? So sulfurous acid, anything that has OUS is typically a weak acid because you lost that oxygen. It makes it a little bit weaker. Okay. So sulfurous acids or OUS acids are going to be weaker. We already know that carbon acids are also going to be weaker. carbon. This here is citric acid. So is that going to be a strong acid or a weak acid?
Weak.
Orange juice. And that kind of makes sense because we drink orange juice, right? Yep. Citrus, right? Citric acid. Yeah. Okay, so if I have if we have this acid, do you guys expect it to be a strong acid or a weak acid?
Is that a P or a D?
What would be the name? What was it? Phosphoric acid? Yes. So it's phosphoric acid. So a general rule that if it's IC, unless it's a carbon acid, it's going to be a strong acid. We also know that that doesn't hold true for hydrochloric acid, right? But that's the exception, right? Okay. So would this be a strong acid or a weak acid? Strong acid. Okay. 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 So if you identify the major species, right? So we know that strong acids are going to do what? Are they going to ionize or are they going to remain unionized?
Ionize.
They're going to ionize, right? So they're going to ionize almost completely. Yeah. Okay. And weak acids, they're going to stay together. They're going to remain unionized. Okay. Okay. So the neutral molecules are going to be basically the major species for weak acids, weak bases, and water. And so we're going to get ionized from ionic compounds and strong acids, and then also strong bases. Okay, so write the formula for the major species in solution for nitrous acid and chloric acid. Okay, so nitrous acid. What is going to be the major species for nitrous acid? So say H and nitrate. So H, NO2. Okay. And what about chloric acid?
We don't put AQ.
Yeah, well, you can put AQ, yes. So for chloric acid, so what would be the major species? Is it going to stay together? Because that's what you're saying. If we put HClO2, and would it be HClO2 or would it be HClO3? Okay. So does it separate or does it stay together? So then the major species should be H3O plus and Cl what? ClO3 negative. Because we know it's chlorate, right? Because it would be hydrochloric if it was. Yeah, if it's chloric, it has oxygen, right? So we have to have this. Okay, because otherwise we call it hydrochloric acid, right? That's just HCl. Okay. And so of course AQ. Okay, questions?
Dr. Henry,
H3O, right? Because it's the hydronium ion, because that's going to be the ion. So it's the H plus that attached to water. Yes, Lucy.
it has a different answer in the spread in the sheets, the packets.
No, say, oh, because it just puts the H. It should technically be H3O plus because it's the hydronium ion. That H plus with aqueous is going to form the hydronium ion.
Okay.
Yeah, sorry about that. So these guys are the same. They mean essentially the same thing.
So do we put
This
a
is before the H plus actually attaches, but it attaches. What was that, Lucy?
do we put a plus in the middle, or do we just separate like?
Yeah, you can use a plus because that means and, right? So like when we do a reaction, you get this and this. What was that? Are you making fun of my arrows? Because we were trying to figure out what that means. So, oh no, this is this here means that they're same thing. They're equivalent. Yeah. So a lot of times, so that we can keep the numbers balanced, you'll see that early on we often use just H to represent the acid. So like say we have hydrochloric acid. We put this in AQ. And then we would just put H plus AQ. Plus Cl minus, right? That's easier than writing out really what it looks like, which is H3O plus, because that H plus binds to the water molecule, right? And since you have tons and tons of water molecule, you're not taking that into consideration into your chemical reaction. Okay, does that make sense? Yeah, no, maybe, or no. You guys have that look. It's that. Questions? No questions. Okay. Yes. That's right. Yes. Until we find something else. That's it. Until we find something else. He says so that trying to have it separate that H plus is always going to go to water, right? Now like yeah, always. Okay, until we find something else. So literally, it's like I think I told you guys before that H plus is kind of like that clingy girlfriend or clingy boyfriend that just won't let go of you. Oh, I love you, I love you, I love you, right? So as soon as it gets in solution, it finds water. It's, oh, I love you, I love you, I love you. They won't let go of water until it finds somebody else. Oh, I love you, I love you, I love you, right? So. Okay. Okay, so up to this point, you guys have learned how to write and balance conventional equations. Okay, so this here is an example of a conventional equation. I can find it. Okay, so today I'm going to teach you guys how to write the total ionic equation and the net ionic equation. So let's start off by, this is the conventional equation. Okay, so in the case of a total ionic equation, we're just going to separate those ions because we know that as soon as you put them in aqueous conditions, they separate, right? So if it's aqueous, they're going to separate. If it's a solid, liquid, gas, it's going to stay together, okay? So in this case, we have lead to nitrate, aqueous. What's going to happen? It's going to separate. So we're going to end up with the lead ion. So it's lead 2 plus AQ. And what else? NO3, how many?
2
Okay, am I going to put in front or subscript?
in the front.
In front. So it's going to be a coefficient, right? Because we know they're only held together by that positive charge. Okay. We have sodium chloride aqueous. What is going to happen there? It's
Separate.
going to split up. So then we're going to have how many sodiums?
2.
So we'll get the sodium ion, which we know is plus AQ. Plus 2Cl, right? 2Cl minus AQ. And then that's going to yield. So next we have PbCl2S. What is that S?
They don't separate.
So they're solid, so they're going to stay together.
Mhm.
So again, solids, liquids, gases are always going to stay together. Okay, and then we have 2 sodium nitrate, aqueous.
So 2 sodiums
Okay,
with a plus charge
okay, with the plus charge.
and 2 nitrates. With a negative charge.
Okay. Okay, so that will be the total ion. Okay. So have you guys ever brought somebody to a party and then they hooked up with somebody and left you there? No? You done it? Okay.
Hey, no, I don't use it.
I think that's, yeah, I think that is everyone's reason, right? Okay. So, but you guys have also been to like parties where, you know, you brought that person to a party and they just stood there and they watched everybody else and they didn't do anything, right? Okay. So those guys are called spectators, right? So they just sit around and they watch everybody have fun and they just sit by themselves and, oh, I'm too scared to talk to anybody, oh, right? And so, in this chemical reaction, we have what we call spectators. I'm going to circle those guys in pink. Okay, so here for this reaction, nitrate is a spectator, sodium is a spectator. The way that we know that is because they look exactly the same on both sides of the equations. Okay, so the nitrate is the spectator because we have the nitrate ion here and we have the nitrate ions here. The sodium is a spectator because it's exactly the same on both sides of the equation. Okay, so those are spectators. So when we take the net ionic equation, we just remove the spectators. I hate doing this to you guys, but I have nowhere else to put it. Sorry in advance. Net ionic equation. Yep. I would if it was working. Right now, everything you can think of is broken down. Everything. You know, you notice that we don't have a little screen anymore, right? Yeah. So I mean, you name it, it's been breaking down. It's just, yeah, we're well overdue for upgrades. Like that. We just got to get money somehow, right? So. Yeah, and the TV went out this weekend. Also, the water and everything went out this weekend. It was a nice event. So we get everything that's left over. So the spectators, we just kind of take those out. So we get the lead 2+ ion plus two chloride ions. And that's going to yield lead 2 chloride solid. Okay. So if we think about it, because those ions, what happens? Those ions go in solution. They find each other. They're like, oh, you're my perfect match. I'm hooking up, right? And they stay together, and water can't separate them, right? They're not weak like the other couple, right? So they're not aqueous, not able to separate. They're a match made in heaven. They stay together, you know? Okay? You guys got it? Someone confident? Yeah, again, if I was able to design a classroom, the instructor would either be up higher than you guys, or you guys would be up higher than the instructor. One of them. Okay, you just remove the spectators, right? So if we take a look, okay, so this here is exactly the same thing over here, right? So in other words, it's not doing anything, right? So it's just kind of sitting there, standing up against the wall. Right? So nobody's gonna remember that. Right? So that's the same thing with the sodium ions. So you just remove them, right? Because they don't make a difference. They're not doing anything. They're just sitting there, right? Where we have lead 2+, and we have the chloride, they come together, right? They hook up. Everybody remember them? Oh, they were getting all solution. summer kid to him, right? Oh, they were all up in the corner, you know, rubbing on each other. Guys, you know you do it, right?
So, okay, so there's at nationals, there's about 3,000 kids all over Australia and everywhere. You got one weekend, you'll never see them again. That's kind of rule at nationals. We're all just in high school, it's just like 1 week, and then you never see them again. The rule is that you find someone from big state, you hang out the whole winter, you never see them again.
Okay. Okay. Are you guys got it? Does it make sense? It makes sense? That's right. Yeah. Okay. So he had asked, since they're the same, exactly the same on both sides, they're spectators. Now, the key is exactly the same. Okay. Okay. So we're going to test your knowledge here in a second. You guys ready? So this is just showing you exactly what we just went over. Okay, so here's your first one. When a strip of magnesium metal is placed in iron 3 chloride solution, a magnesium chloride solution results and solid iron forms. Develop the net ionic equation for the reaction. What I want you guys to do is start off with the conventional. Then I want you to give me the total ionic equation. And then I want the net ionic equation. Okay. So let's start off with the conventional. So what is the chemical equation, the conventional chemical equation? So what does magnesium metal look like? MgS. And that's reacting with what? FeCl3 AQ. How did you know it was aqueous? Because it says solution. That's right. Okay, and that's going to yield so you said MgCl. And okay, is that balanced? No, what do I need to do to balance it? Okay, but is that the first thing that you do? So let's work it out. So let's, yeah, we could all look at the answers. That's the easy part, right? But we want to make sure that we got it, right? Okay, so how many magnesiums do we have on our reactant side? On our product side? How many irons do we have on our reactant side? And on our product side? How many chlorines do we have? And okay, is that balanced? Okay, what do I need to do to balance it? 3 in front of where? 3 in front of the Mg. Okay, why do I need to put a 3 in front of Mg? Ah. Okay, so then I have 3 here, and I have 3 here. But now I have 6 here. Is that balanced? 2 here. Okay, so that gives me 6 and 2. Okay, so now we have it balanced. Okay. Okay, now what about our total? Let's go through. Can I erase this? Yeah, we don't need this. Oops. I erase everything. Okay, now our total. So magnesium, what are we going to do with that? We're going to leave it alone, right? So we're going to put 3 Mg, and it's a solid. Okay, what about our iron 3 chloride? It has a charge of +3, so I have a coefficient of 2. That's right. And then I have a +3 charge. And we put AQ. Okay. Now, what else? Am I done? I have the chloride ion as well. How many chlorides do I have? I have 6. Since they're separated from the iron, they're going to be separate, right? So that's why we have to use the coefficient. Then that's going to yield so we're going to get 3 Mg. Is it going to have a charge, or is it going to be? What is the charge on magnesium? +2. Aqueous. And and okay. You guys see that? Yes. Because it's the element, right? And all elements on the periodic table are neutrally charged. Good question. So let me repeat the question. So the question he asks is, why doesn't this first magnesium have a charge? It's because it is the element, magnesium metal. All elements on the periodic table are neutrally charged, right? That's right. It has no charge because the electrons balance out the protons. We learned that the very first week or second week, right? Okay. Okay. So my next question is, who are my spectators and why?
Chlorine.
You said the chloride ions. Okay. So the chloride ions are the spectators. And you said because they're exactly the same state, negative charge, on both sides, where the magnesium starts off as neutral charge and becomes an ion. Okay, so then my net ionic equation are going to be those that are just left over after we get rid of the spectators. So that's going to be 3Mg solid plus 2Fe 3 plus and that's going to yield 3Mg 2 plus plus 2Fe solid. Okay, questions? No questions?